Welcome to this lecture in the ongoing series of lectures in real analysis. Today we will be discussing the notion of Riemann integrability. So far we have discussed, well, quite a lot of things. Let me recall the things which are pertinent to this lecture, at least some of them. So suppose we have a continuous function defined on a compact set. So whatever was the definition of a compact set, we proved that they are same as closed and bounded sets, and ultimately therefore closed intervals are also compact. So closed intervals are special cases of compact, special examples of compact sets. Alright, so suppose we have a continuous function on a compact set, then we saw that f is uniformly continuous and that f achieves its supremum and infimum, meaning it has a maximum value and a minimum value. So this is the formal enunciation of that. And last time we saw Darbaux's theorem. What I was calling Darbaux's theorem. This is not the pronunciation. It's a French name, I suppose. So it's probably Darboux or something. But I might continue to call it Darbaux because that's how I've been calling it for a long time. Alright, so we have a bounded function. Then what we saw was that this thing holds, which means, let me expand on what that meant, which means that for all epsilon greater than 0 there exists delta greater than 0, such that whenever we have a subdivision sigma whose norm is at most delta, or rather strictly less than delta, we have this difference. There is no need for absolute values, but doesn't matter. We have that. So that's what this means, right? Similarly, we have that for the lower integral, and forget about this. We will cover that today. Okay, so we have this much on the table. Now let's go on to the material of this lecture. Okay, so we'll define what is called the oscillation of a function corresponding to a subdivision. So we start with a bounded function as usual and fix a subdivision of the domain. Then we define the weighted oscillation of f corresponding to sigma as this quantity. So it's not really a fundamentally new concept. It is just an auxiliary concept which makes life easy. That's the only reason why we're introducing it. Again, this f may be dropped, but it looks a little bit more beautiful if we put it. So we have this definition. It's a very simple definition. Although we call it the weighted oscillation, I might just call it oscillation in future and assume that this is understood that I mean weighted oscillation. So we have defined oscillation or weighted oscillation, and thus by Darbaux's theorem we can write this. Yeah, immediate from Darbaux's theorem. Okay, so here is a lemma. Again, we have the same this setup. I'm not repeating that. The lemma says the infimum over all subdivisions of the weighted oscillation is the difference of the upper and the lower integrals. So it shouldn't be a surprise, but let us give a formal proof. Oops. Okay, so let W equals this infimum, just a notation. then since we have W F sigma equals S sigma minus little s sigma, by definition, we have this is greater than equal to the upper integral minus the lower integral. So this we immediately have because this is greater than that and this is greater than that because this is at most that. So since there is a minus sign, this is greater than that. So therefore this is greater than that. Greater than equal to, I mean. Okay. So if you take the infimum on the left side, we get W is at least the difference. So that's half the story. Now for the reverse containment, we'll use Darboux's theorem. So let sigma n be a sequence of subdivisions of the domain such that the norm goes to 0. Then W sigma n is this thing, which by Darboux's theorem goes to the upper integral minus the lower integral as n goes to infinity. So therefore the infimum of W sigma over all subdivisions is at most the limit. Well, okay, so it's at most the infimum when n goes from 1 to infinite, because the subdivisions that we get for n is equal to 1, 2, 3 and so on, of course, form a subset of all the subdivisions that you can get. So infimum over all the subdivisions, of course, is at most this thing. The bigger the set over which we infimum takes, the smaller the value becomes. So we have that, but this is equal to the difference of the upper and the lower integrals immediately because of this statement. So this implies that, which is W. So what we get is W is less than equal to the difference of the upper and the lower integral. And if we combine these two things, we get the desired result. So just a consequence of Darboux's theorem. Okay, so we have some concept known as oscillation, and we prove some basic things about it, and now let us use that. So now here is the main concept of this module. So a bounded function defined on a comma b is said to be Riemann integrable if the upper and the lower integrals are equal. So last time we saw basically that as an example, we saw that this function f, the function f from 0, 1 to r, which takes x to x, is Riemann integrable. I calculated the upper integral, and similarly one could calculate the lower integral, and that also turns out to be equal to half. And therefore this was one example of Riemann integrable function. We will prove a general theorem here about Riemann integrability of all continuous functions defined on closed intervals. So this was just a special case of a Riemann integrable function. Alright, so if f is Riemann integrable, then we define the integral of f as, well, this is the notation, and we may define it either as the upper integral or the lower integral because they are equal by definition of Riemann integrability. So we have defined Riemann integral. Okay, so as a piece of notation, we may denote this as this also, and there's a good reason for this notation. I will get to that. Why is this even introduced? There's a very good reason for this notation, but right now just let us take this as a snippet of fact that this may also be denoted like this. In fact, in high school, this is how we used to write integrals. Anyway, so not all functions are Riemann integrable. As an example, the function which takes 1 on irrationals and 0 on rationals is not Riemann integrable. We saw this because the upper integral will turn out to be 1 and the lower integral will turn out to be 0. Okay, so fine. Let's prove a simple criterion of Riemann integrability in terms of oscillation. So let f be a bounded function. Then f is Riemann integrable if the oscillation tends to 0 as the norm of sigma goes to 0. So if you, okay, so what does this mean? Of course, this is somewhat informal. This means that for all epsilon greater than 0, there exists delta greater than 0, such that whenever the norm of a subdivision is smaller than delta, we have the oscillation corresponding to that is less than epsilon. The oscillation is always non-negative, so there is no need for absolute values. Okay, so this is what we mean when we write that. All right. So, well, okay, so let us, I mean, I'm sure you see this immediately, but let me do the full details. So first assume that the limiting condition holds. We want to show Riemann integrability, so let the difference between the upper and lower integrals be equal to alpha, and then the oscillation, or rather this infimum, would then, or in fact, okay, so here is the thing. So then S sigma, this is of course greater than equal to the upper integral, and S sigma is less than equal to the lower integral. This is a very, nothing to do with the situation. This is a very general thing. So therefore, this thing is greater than equal to alpha, because you just once you apply by the minus sign, this gets reversed, and then you add it, you use this notation, and you get that. So we have that. This is for all sigma, and therefore infimum of sigma, what is this? This is W sigma. So therefore infimum sigma W sigma is at least alpha, because if this happens for each sigma, therefore it will also happen when you take the infimum. So we have that, but infimum of sigma of W sigma is 0 by this assumption. The infimum is 0, so this implies alpha is 0, and we have Riemann integrability. Okay, and similarly the other direction, assume Riemann integrability. That is, the upper and lower integrals are equal. And we want to show that this limiting thing happens. Okay. So fix epsilon greater than 0. So by Darboux's theorem, there is a delta such that whenever the norm of a subdivision is smaller than delta, we have both the things happening simultaneously. And since we are assuming this, I may drop this bars, because this is then equal to, by notation, that. Okay, so we have that, and now therefore, okay, let me put an epsilon by 2 here. That would be better. So therefore, whenever norm sigma is less than delta, we have, I'll just add the two things. I'll get S sigma minus little s sigma is less than epsilon, and which is same as saying that W sigma is less than epsilon, and that's it, which is same as saying the above statement is same as saying the limit of the oscillation is 0 as the limit of the norm, as the norm goes to 0. Okay, fine. So we have again some, nothing very special is happening. It's just Darboux's theorem repackaged. Fine, and now we can use, we can get to some concrete stuff. So here is our first general family of functions which satisfy Riemann integrability. So let f be a bounded monotone function then f is Riemann integrable. Right. So this is a general class of, it's a big family of functions. Every bounded monotone function is Riemann integrable. So let's prove it. Okay, so for each k, for each k, define sigma k as a naught, then a naught plus b minus a by k, a naught plus twice of b minus a by k, and so on up to a k. So okay, so this is also something we will write in this fashion. All we are doing is we are partitioning the closed interval into k equal parts. This is a0, which is equal to a. This is ak, which is equal to b. And then there are some equipartition. Okay, let me draw it this way. This is a1, this is a2, and this distance is b minus a upon k, meaning this whole length divided by k. So we have just partitioned our interval into k equal parts. Clearly then the norm of sigma k goes to 0 as k goes to infinity. Fine. So what is the oscillation? What is the oscillation corresponding to sigma k? So this is equal to s sigma k minus little s sigma k. And okay, fine. So I'll do it only under the assumption that f is an increasing function. One can similarly give a proof for decreasing functions. So I'm assuming f is increasing. Assume, or let me write it here. Assume f is increasing. Yeah, so what is s sigma k? S sigma k is summation I equals 1 to k mi times b minus a upon k. So what is happening? Mi is the supremum of f on the ith part. So m1 is the supremum here, m2 is the supremum here, m3 is the supremum here, and this is the length of the ith part. Each part has the same length, so I have just written it like this. But what is mi? Now here we use the fact that f is increasing. So if f is increasing, then the supremum of f over this region is achieved here, and the supremum of f over this region is achieved here, and so on. So this is just summation I equals 1 to k f of ai b minus a upon k, and similarly little s of sigma k is equal to summation I equals 1 to k f of ai minus 1 b minus a upon k. So now the difference is, a bunch of things cancel out. Only the I equals 1 term here remains, and I equals k terms here remains. Everything just cancels out if you take the difference. So this is equal to f of a k, which is equal to b minus a upon k minus f of a b minus a upon k, which is, well, fb minus fa is just some number, b minus a is just some number, and this number is divided by k. Therefore, so this quantity is equal to that by definition, and therefore limit k tends to 0 w sigma k equals 0, and that's it. That shows that the function is Riemann integrable, because By Darboux's theorem, this limit converges to what? This limit converges to the upper integral minus the lower integral, which is 0 by our proof. So that's it. Okay. So bounded monotone functions are integrable. And now for the other family that is very interesting is the family of continuous functions. So lemma, or theorem if you like, be a continuous function. It will automatically be bounded because continuous functions on a compact set are bounded. So let f be a continuous function. Then f is Riemann integrable. Okay, so here is we have the same story for each k. Define sigma k as we did previously. Okay, so we have just defined it the same way as we did previously. And let me, so here is some some function, and what I want to say is that f will achieve its supremum in every one of these chunks, because each chunk is a compact set and f is continuous on that. Therefore f will achieve its supremum somewhere and f will achieve its infimum somewhere. So to that effect we define fixer k and define yi star, or rather than define, let me say let yi star in the ith part be such that f of yi star is the supremum of f on the ith part, which so far we have been writing as mi, and similarly let xi star in be such that fxi star equals infimum. So I'm just developing some notations here. Which we have been writing a small mi. So this is for a k. And there, I mean, one should really put a k here somewhere so that it is clear that, you know, the dependency of yi star on k is clear if we put a k here somewhere, but I'm not doing it because then there are too many subscripts and superscripts. Okay, so these are just some notations so far. We have done nothing. We haven't even really exploited the continuity too much. except for this fact that we can find a yi star which matches the supremum. Okay, so now we want to show the following. We want to show that to show Riemann integrability, we want to show that limit k tends to infinity, w sigma k is 0. If we show that, then we are done, because this is what we have been doing so far. So I hope this much is clear. So this is what we want to show. And now we will exploit the uniform continuity of f. Okay. So to show this, fix a epsilon greater than 0. And we want to find delta such that we want to find a capital K such that whenever little k exceeds capital K, then this is at most epsilon. So we proceed to do that. So let k be such that, or even before that, by uniform continuity of f, there is a delta such that whenever x and y are less than delta apart, we have the corresponding images are less than epsilon apart. This is immediate from uniform continuity of the function, because the function is continuous on a compact set. It is also uniformly continuous, and we've just exploited that. And now we will locate our k. So now let k greater than equal to 1 be such that b minus a by capital K is less than delta. So we can find such a capital K by Archimedean property. Alright, so now fix little k greater than equal to capital K, and we will show that the corresponding oscillation is less than epsilon, which will finish the proof, because then we will have established this. That. Yeah. Okay, so here is how we go. We have S sigma k is, well, summation I equals 1 to k mi sigma k b minus a by k, because that is the length of each part in sigma k. And in our notation, this is equal to fyi star b minus a by k. So this is just the notation that we developed, exploiting the fact that a continuous function on a compact set achieves its supremum. And little less sigma k is equal to this summation. Alright, so we take the difference. And now yi star and xi star are both in the ith part. So here we have the ith part somewhere. This is ai minus 1, this is ai plus 1. This length is less than delta because this length is 1 by little k, and 1 by little k is smaller than 1 by capital K. Sorry, this length is not 1 by little k, this length is b minus a by little k. Let me write that again. So this length is b minus a by little k, which is less than equal to b minus a by capital K, which is less than delta. Xi is here, xi star is here, and yi star is there. I mean, both are there in this interval. So, of course, the difference between xi star and yi star is at most delta. They are both lying in an interval of length whose length is less than delta. So xi star and yi star are less than delta apart, which by the uniform continuity, which by the choice of delta, tells us that this quantity is less than epsilon. So this is less than 1 to k epsilon b minus a by k, which is equal to epsilon b minus a. So let me erase that. Fine. So okay, maybe I should have put an epsilon. I mean, here I should have put b minus a. Just but I mean, what I've done is not wrong. So what we have is, therefore, S sigma k minus the oscillation corresponding to sigma k equals this difference, which is less than epsilon b minus a. And what this shows is that as we take the limit k going to infinity of the oscillation, this is 0, because we just fixed an epsilon and we showed that if little k is large enough, it is larger than some capital K, then we have this estimate, which means that this thing will go to 0 as k becomes bigger and bigger, because b minus a is just some constant. Okay, which shows Riemann integrability of our continuous function. So all continuous functions on compact, or rather just closed intervals, are Riemann integrable. Okay, so lastly, I will leave you with an exercise. I'll also probably put this in the problems maybe, but here is an exercise, is that let this be a bounded function, then okay, and let C be some intermediary point, then F is Riemann integrable if and only if both these restrictions are Riemann integrable. So you just use Darbo's theorem and you'll get it. As I think we saw the last time, that this integral, this upper integral is same as, yeah, we saw this. So in fact you can just use that and you will have your answer. Similarly for the lower integral, and you will get this thing. So by restricting Riemann integrable functions to sub closed intervals, you again create another Riemann integrable function. This is not a surprise. Okay. So yeah, I think this is all. So as usual, like, comment, share, subscribe. I also have Patreon. See you next time.